To find the position of section where the shear force will be 0, put equation number 6 is equal to 0. This is our equation number 6. Why we are choosing this? Because this equation is explaining or giving the value of the shear force up to this mark, up to the inner face of the column A. And this is approximate that the shear force will be 0 between these 2 points A and B, and there is no load after the A and before the B. So if the point is lying in between, so we will consider equation for shear force as equation number 6, right? So equating this equation is equal to 0. We don't know the position of x where the shear force will be 0. So we're putting the whole equation is equal to 0 and find a value of x is equal to 3.55. So this is the location where shear force will be 0, and we know that where shear force is 0, the bending moment will be maximum. So now here we are going to make an equation for the bending moment at any section x is given by mx is equal to, we are considering any section x at distance x. So what will be the bending moment here on this particular section? In that case, we will consider the total upward pressure up to this area and plus the moment due to the external load 600 kilonewton, right? So in our case, we will take hogging as positive, sagging as negative. So 600 kilonewton is how much away from the section x is x minus 1. So here it is the distance x, and x minus 1 is the location of 600 kilonewton, which is away from the location x1 and x2, right? And same, because it is create hogging, we are taking it as a positive, and the rest equation will be negative, which is creating a moment due to the upward swell pressure. Now, the maximum hogging bending moment m1. It will occur where the shear force is 0. There the bending moment will be maximum, means at the location x is equal to 3.5 meter where the shear force is 0. So here this is the value of the m1 maximum bending moment, which will be hogging, right? Okay, now to find the value of x where mx is 0, now we have to calculate the point of counterfracture. To calculate the point of counterfractures, we are just equating this equation of bending moment, which is for the at any section x. We are equating this equation is equal to 0, and we will calculate the value of x where the bending moment will be 0. That will be your point of counterfracture, right? We are equating this equation is equal to 0. Please read this carefully to find the roots, because when we calculate or solve this equation, this will be the cubical equation x cube plus x square plus x plus something constant is equal to 0. To solve this equation, please read. To find the roots of above equation, first simplify the above equation by taking LCM and then calculate its first root by trial and error method, and the remaining two roots will be calculated by using quadratic equation. You will get the following roots. You will get the value of x1, x2 and x3, and it is 1.15, 1.70, and this will be minus 20.445, which is invalid due to negative sign. So we will consider these two values, right? Above values are positions of point of counterfracture where the bending moment changes the sign. We can say bending moment will be 0 at the particular location. Okay, so now to find the shear force 3 at the first point of counterfracture, put x is equal to 1.15, and at location 2 put x is equal to 5.70. Put these values in equation number 5, and we will get the shear force at the particular locations, or at the point of counterfracture 1 and again at the point of counterfracture 2. Right, we will take obviously upward sign as a negative, upward forces as negative, and downward forces as positive. Now we will calculate the shear force at different particular positions. First, the shear force at inner face of the column B, where the x is 5.8 meter. This we will calculate from the geometry, because we know the CG location, we know where the shear force is 0, so we can calculate easily the location of x due to these particular locations, right? Shear force at inner face of the column B is here, and we will calculate the x from this point to this, right? So for this we are again using the equation number 5 and just putting the value of x, and we will get the value of shear force 5, which is at the inner face of the column B, similarly outer face of the column B. And here we are going to calculate sagging bending moment, which will be moment 2 at the outer face of the column A, is obtained by putting x is equal to 0.85 in the second term of equation number 7, right? This is our equation number 7, which we already made to calculate the bending moment at any section of the footing, right? This is equation number 7. I'm just reminding. From that equation, we will get the value of M2, that will be 47 kilonewton meter, and sagging bending moment for the cantilever portion to the right of the column B is given by putting the value of x is equal to 6.2 up to this position from this location. So we will get bending moment 3 at the outer face of the column B, that will be 117 kilonewton meter. Now draw the bending moment and shear force diagram. So here we made the bending moment diagram. We are just taking all the positive values to the upward side of the reference line and negative, or we can say sagging bending moment in bottom. And here the diagram for the shear force, right?